Thank you. If you're sitting such that you have problems seeing some edge of the screen, please try to find a better seat, because I'm shamelessly going to make use of every single pixel on there, just so you know. Welcome. I don't like this code. You've probably seen code like this. It's not bad code. It's not problematic. It's nothing particularly wrong with it. And if you ask me, if you sent this code to me for a code review, I wouldn't complain. So it's not wrong. But it annoys me. And what annoys me is this repetition, this state equal equal. It's like a religious mantra that you have to repeat over and over, and it doesn't add any information. It's just ritual, and that annoys me. I should say that this repetition is not what we're talking about when we're talking about the dry principles of software design, that don't repeat yourself. The don't repeat yourself is about avoiding repeating the same kind of logic in several places in your code base, which makes it difficult to make changes, because you have to remember to update all those places, and you will fail and you will introduce bugs. So this is not it. This is not a problem. It's just annoying. So welcome all to Modern Techniques for Keeping Your Code Dry. I'm Björn Fahller. I am professionally and avocationally annoyed with code. I work for NetInsight in Stockholm. We make networking equipment, everything from mechanics design to network management systems. We're hiring, just putting it out there. Talk to me if you're interested. I'm also very active in the Stockholm C++ user group. So if you're in Stockholm, get in touch, geek out with like-minded people, maybe do a guest talk at one of our meetups. So with that out of the way, the talk is about techniques. And I'm going to drive these techniques with an example that is arguably quite silly. Bear with me. It will hopefully be fun. The techniques are not silly, though. So we're at this. We have this annoying assert state equal equal idle or state equal equal disconnecting. I said I work with networking. What can we do about reducing the repetition here? So one thing that occurred to me fairly early was to use a variadic function template. So I can write something like that. Is any of that takes a state type and a variadic number of values to compare it with, and we return this fold expression. So are you familiar with fold expressions? Anyone not familiar with fold expressions? A few hands, okay. The fold expressions are your friend when you're dealing with variadic templates with parameter packs. Because what this means, this highlighted section, this parenthesized expression, is that we say that this s equal t's, this compares the value of s to the first value in the t's parameter packs. This is ORed with, and ... is all the other values of t's in the parameter pack. So you repeat this s equal the first value, or s equal the second value, or etc. In C++ 14 and earlier, you had to, if you wanted to express this, you would either have to do a recursive construction that can kind of hurt your mind a little bit and definitely hurts your compile times. But fold expressions get away with this. You can also do really ugly cheats in earlier versions of C++ with initializer lists and whatnot, but I don't want to go there. Fold expressions are your friends. So then we can write code like this. Is any of state idle, disconnected, and disconnected? And this is absolutely horrendous. I mean, 8 out of 10, sort of, for getting rid of the repetition, but minus 10 million for making the code unreadable. Because this doesn't, when you see this, assert is any of, it doesn't help you. It doesn't give you any guidance to is any what or what. how are the arguments connected to each other? What does it mean? The only way you can know what it means is to read the function body. And that is a failure, in my opinion. So if you gave me this in a code review, I would definitely have a few words. So, okay, it was worth a shot, wasn't it? A variadic non-type template parameter function template. Sneaking that in a conversation in the bar. It's quite a mouthful. What I mean is that we take template non-type parameters. That is what you have on top there. We say that we are repeating values of state type over and over. So normally with templates, the normal case is to almost always is to use types, but we can use non-type template parameters like these. It doesn't work for all types, but it works for enumerations. It works for integers and a few other types. So then we can write it is any of idle, disconnect, and disconnected state. We can generalize it a little bit further. If we're in C++17, we have this availability of writing template auto, ... Let the compiler deduce what the type is. So I don't have to say that it is explicitly state type, which means that this is any of function is now generalized. It's not tied only to this state type. We can use this for any kind of value that we want to check if it's in a range of. So that is useful. It saves some repetition there. This is good. But not all types can be used as non-type template parameters. We cannot use strings, for example, not currently. And we cannot use anything that is computed at runtime, because this must be a compile time property. And yeah, the last one is maybe a little bit silly. It's a thing of mine. I'm happy when code reads like normal conversational English, and this, like Yoda speaks, sounds. We understand it, but it's backwards. And yeah, sure, so most people don't care. Good for you. I'm unfortunately one of those who feel a little bit uncomfortable when I see that. But it works. It's good, because this expresses intent in a very good way. You can have a very good hunch of what that line means without looking at the function body. So from that point of view, it's good. But we can maybe do better. We can construct an object and then test on that object. So there was something of a little bit of a competition a few years ago on Twitter on who could make the smallest test for if a value is one in a set of values. And I'm fairly happy with my contribution to get both the implementation and the Godbolt link in. Mind you that this is when tweets were limited to 140 characters. Okay, so Twitter is not the best IDE in the world, so the code is maybe not so well formatted, so we can clean it up a little bit. So we have is in that takes some type that returns a lambda. The lambda takes a number of values and returns the result of the fold expression that you've seen before. So when we say is in state, that is this lambda. So that, by the way, is one of the things. C++14 gave us the possibility to have auto-return type on functions, and that is probably the greatest thing ever. Because then you can return lambdas that captures the function parameters and does something that is so great for composability. We'll return to this a lot in this presentation. So we have is in state, that is this lambda, and then we call it with these parameters, idle, disconnect, and disconnected. Those are the function parameters that gets into the fold expression. This works with all types for which the expression makes sense. So that is good. It looks absolutely horrible because it's too terse. It's missing information. It's failing to convey information to the reader of the code. But I think we're edging our way towards something that is useful. Not quite there yet. But we can be more explicit and construct something with a named compare function. So if I have a templated struct is that takes a t, and we have a templated member function any of that takes a number of parameters and does the full expression that you have already seen a number of times. And then from C++17 we have constructor template argument deduction, CTAD, which means that if you can construct a template with parameters without actually explicitly naming the type in the template. Sometimes you need a guide for that. So that is what this is. What this means for the compiler is that if you see something that looks like a construction of is with a value t, then it means that we want to construct an is of type t. The guides can be useful for other things, like say if you have iterators or whatever, then you probably want to construct your type from the value type of the iterator, so it's not always this obvious. In most actually cases, the compiler can deduce a type without the deduction guide. In this example, I could have used a constructor, and then the deduction guide wouldn't have been necessary. But these are good. These can help us a lot in writing code that is very generic and not very verbose. If you're not familiar with CTAD, you should watch these presentations from CPPCon last year. So, Stefan Lauerwaite's talk about class template argument deduction for everyone, it gives you a really good introduction to what all this is about and how amazingly awesome it is. And when you're all stoked up and super enthusiastic, you watch Timur Dumner's talk and see that it's all a trap. It actually isn't all a trap, but there are some things to be aware of. So with this, we can now write is curly state any of idle, disconnect, and disconnected. This still works with all types. It's very explicit. I like that, because we can see that is state any of these alternatives. This is good. It's still Yoda speak, so it annoys me still, because I'm like that. But it's useful, I think. We're getting somewhere. But it's not important. Time passed. And your mildly annoyed developer stays annoyed. And then 2 years later, a little more than 2 years later, I use the awesome IDE of Twitter again. Now the limit has been lifted to 280 characters, so I can write really verbose code. So we have a class any of that is a tuple, and it has an operator equals that returns the fold expression that you've seen. So at the bottom you can see is any of 135 equal x. Yoda, but it's kind of cool. So I'll talk you through this. So we have our any of that uses private inheritance from tuple. This is only because I'm an extremely lazy person. It really should be a member. But tuple has 18 constructors, 18. And just by saying, using the tuple of t's tuple, I get all those constructors. They just come to me. I don't have to care. And it doesn't change anything, I think, for the user of any of, but it saves me work. So that is good. And then I can use std_apply. Std_apply is a real friend for when you're doing generic programming and you have parameter packs and tuples. Std_apply takes something that is callable and a tuple. And it calls the callable with each of the elements of the tuple as the parameters to the call. This is absolutely awesome. Unfortunately, since the inheritance is private here, and std apply is not a friend. It cannot see that star this is a tuple, so we need this ugly cast. That is unfortunate, but it's an implementation detail. No one has to see it, so that is good. And then we need, well, don't need, but we want to make a friend with the symmetric reversed order operator equals. So now we can write is state any of idle, disconnected, and disconnected. And I am unreasonably happy about this code. This is amazing. This nerd heart is beating. This is cool. It is cute. It is maybe exaggerated. But I really like this code. I'm sorry, I really do. Let's have a look at, I mean, we are C++ developers. We care about performance. It's not just, is this cute? Is it actually a good thing to use? So let's find the right one. So we have our state type, any of, looks familiar. And we introduce some class that has a state type and a function. And I'm using the preprocessor here to divide it into two versions. One that's written the traditional way with the annoying repetition, and one with the any of. So here I have defined this plain macro. We see the code generated, and here I don't have it. So I don't know, I cannot see a heck of a lot of difference in here. Yeah, there is a difference in the line number in the assert, that makes sense. The strings in the assert are different, that makes sense, but the code is identical. So the compiler couldn't do a better job, possibly. This is the same thing. That is neat. So there may be a number of reasons to not want to use this construction, but fear of performance is not one of them. Then we can, of course, add some more, because why just operator equal? I mean, we can do other things, like less than, and greater than, and less equal, and greater than equal, and not equal. And so I can write this loop like that, and this is just amazing. This is so cool code. I'm really happy with this. So maybe this becomes a problem, though, because it's more convoluted. Let's see. So the same construction, operator less than, this while loop. Yeah, the compiler seems to get it. Not really unexpected, but good to know. Okay. But we have a problem. I set out to solve something that was at most an aesthetic problem with repetition that looked ugly, and now I created a real software engineering problem with repetition. Great job. So yeah, these green blocks are the only difference between these two, and it's much worse than it looks like. You see these dots? That's less equal, greater than, greater equal. This is terrible. Maybe I shouldn't do this software engineering stuff. I'm not quite cut out for it. Bummer. But maybe we can add another level of indirection. So this function or element, so that it just takes something callable f and a tuple. And it does to apply on a lambda that calls this function for every value in the tuple ORed with each other. So we have this fold expression that you've seen before, but we have lifted the level of abstraction so that I can generalize and say, or these expressions with each other, these functions. So now I can write instead operator equal equals is or elements of a lambda that just checks for equality, and operator less than is or elements of a lambda that just does less than. It's still a bit of repetition, but it's a lot less. So we're getting somewhere. That is good. Maybe we should check. We added yet another level of indirection. Maybe we caused some performance problems. Better have a look. So have our OR elements. We use OR elements with the fold expression here. Yeah, and look. Yeah, you can see that it's called. It's blinking on the right. And it seems to be generating exactly the same code still. So we're still good. All right. But what if we want to add this also an each of instead, in addition to any of? To repeat everything again? That is not really what we want to do, is it? So, as always, you add yet another level of indirection. So I make my OR elements not a freestanding function, but a type that has a named static function. I don't think apply is the right name, but never mind, it's what I used. And it's the same implementation as before. And then I have this opt, and Kate Gregory is going to give me a very stern talking to about my namings. But bear with me, these are implementation details. The users will not see it. So I have opt that takes an operation and the t's, and it's pretty much the same as before, but you see this operator equal equals now calls op : apply. So this is good. So any of now inherits from opt of or elements. So that is good. And you can use an each of that uses an and element. And I created a whole new bunch of functionality with very little code. That is good. I like that. In a better world, I would be able to use constructor template argument deduction for type aliases, and I would just write like that. But unfortunately, we are not in that world. So otherwise, this template at the bottom, the each of template would not be necessary. We just use an alias, but it doesn't work that way. It's not my fault. Actually, it is my fault because I haven't proposed anything for the committee. Let's look. So have our and elements, our opt. Bummer, all of. It should be each of. Sorry. The perils of updating slides. But yeah, they're still the same. That's good. We're home dry. Yeah, good. So we don't have to worry about that. The compiler is still able to see through this. So, questions so far? By the way, don't be shy to interrupt with questions or whatever if you think I'm blasting through too fast. Sorry? GCC is the same, and MSVC, to my great surprise. Why did I use libc++ instead of I use this normally when I do presentations because some of the libstud C++ implementations of algorithms are extremely clever but generates hard to read code, whereas lib C++ produces easier to read code. But I can change this. Whoops. So I can use this one. And yeah, doesn't really matter. And I can use GCC also, that is not a problem. You can be adventurous and go back to a little bit older one. It's the same. Doesn't matter. Do I always copy? Was that the question? Oh, I hoped I wouldn't get that question. Because if I change the reference, the performance may change. I will show you something later when we go to depending on how much time we have, or in the discussion zone after, I can show you. I used value because I want to simplify the slides a little bit. And there is a performance issue with using values if your type is non-trivial. These are integers for all intents and purposes. So that is very simple. If I use, say, strings, copying strings is expensive. So you would have to use a little bit of trickery there. But it complicates the slides to the degree that I don't want to do. So we can discuss this later. It's manageable. Okay, the infamous compilation error question. I'll address that towards the very end. For now, write correct code. Okay, I think lambdas are really cool, in case you haven't noticed. So I'm actually going to start all over and do the same thing again, but with lambdas galore. So here is a tuple. It may not look like a tuple, but it is one. So when I call tuple with ABC, that is this lambda. It has captured ABC. It is callable with a function. This function is then called with all the captured values in the tuple. So the function can be, for example, return the first element, return the last element, return the nth element, return the number of elements, whatever. It's an amazingly crappy tuple, but it is a tuple. We can use it. Yeah, so in this case, we call this tuple with this lambda that does the fold expression that you've seen before with that, in this case, each element is greater than 0, logically ANDed together. So this last line reads A greater than 0 and B greater than 0 and C greater than 0. Right? And then we can have our AND elements also as a tuple. AND elements takes a function that it remembers, captures the function, and then we call it with a number of elements, and it does this fold expression, logical AND with the function called for each of the element in the call. So this is useful. We can combine these. So now we can call tuple ABC with AND elements and a simpler lambda that just checks, is the value greater than 0? And that value is, that lambda is now the func in this instantiation of AND element. And the whole AND element is now the function that we call to tuple. So with still this line, the assert at the bottom still reads A greater than 0 and B greater than 0 and C greater than 0. So this is neat. We can compose things. And then I have a bind RH for right hand. The C++ standard library will hopefully get a function, a higher order function bind front that takes a function and a number of parameters that it binds. And then when you call it, it will call the function with the bound parameters and the extra ones that you add to the call. But it lacks one for binding to the back. And ideally, I would have written a generalized bind back function here, but for in the interest of brevity in the presentation, I assume that function is a binary function and just binding the right-hand argument. So this returns a lambda that is callable with one parameter, and when called, it calls a function with the bound, with the call parameter and the bound parameter. And this is useful because then we can write, for example, greater than by bindings to the greater and the value. So we can write greater than 0, and that is callable with something, whatever, and it will return whether that something is greater than 0 or not. Now I have the building blocks. This is Lego. So we can say this tuple A, B, C and elements greater than 0. We're getting to something here. So and elements greater than 0, you can see this composition, how it works. So this still reads A greater than 0 and B greater than 0 and C greater than 0 through all these indirections. So now I can use these. We have these, the tuple, the and elements equal to and greater than, and I have my gloriously named opt, which has a tuple and a function. And then I have this each of lambda that just returns an opt of and elements and tuple. The constructor for opt takes something that is callable, that is and elements and the tuple, and stores them as member variables. When we then call greater than 0, it returns apply greater than t is 0, and apply is this function that does this indirection via the func that was and elements. So a lot of indirections in here. Could maybe mention that with C++20 we're probably getting a no unique address attribute. This actually isn't really necessary in this case, but it's a bit wasteful. If, as in these examples, the functions don't have any data members, they shouldn't really take any space. But the type rules of the language says that all objects must have unique addresses unless they are related somehow. Which means that this one, even if it's absolutely empty, will take at least 1 byte, and then you have alignment issues, so this type will be unnecessarily large. If you're on earlier C++ versions, you can use ugly tricks like private inheritance to use the empty base class optimization, because then the types are actually related through inheritance, so they can share address. This is so cool. The functional composition with lambdas is amazingly powerful. Let's see. I'm running really, really fast. Sorry. Let's see what this does, because now we have a lot of indirections through lambdas. So we have our tuple, or elements, bind right hand, equal to, less than, our opt with operator equal, operator less than, we have an any of. I changed this example a little bit. I have a function, whitespace pos. It takes a string view and returns the position in the string view of the first whitespace character, or -1 if there isn't any. And So I'm writing find if in the range of the string something is equal to any of tab, line feed, character return, or space. I really like this code because this says what I want. I say I want an iterator 2 because that is what find if does. A position that is equal to where the value is equal to any of tab, line feed, character return, or space. That is amazing. So let's see what the compiler does with this. Okay, so we get RDI, we check if it's 0, I guess that is, we jump to 5, so that is where we leave, right, yeah. So RDI is apparently the length of the string view, okay. Then we get a really huge value. Any guess of what this can be? Never mind, we'll go on. Okay, so we'll read RSI and RDI again. Kind of unnecessary, I think. We'll get a value from okay, that's the first character, compare with 32. 32 is what character? Space, okay. So if it's before, jump BE, if it's unsigned before, that is, it's 30, before or equal. If it is 32 or less, we jump here and do a bit test. Okay, that's interesting. We do a bit test of the character value in this huge thing. What is this? Yes, it is not NPOS. No, this is a bit mask. It has the bits 9, 10, 13, and 32 set. How well do you know your ASCII values? Tab is 9, line feed is 10, character return is 13, space is 32. That is what this is, a bit mask for these values. Why? Because it can make the logical OR of 4 comparisons as one instruction. That is why. And then it goes on. So compilers are pretty darn awesome. This is amazing. This, I must admit that when I prepared this example, I did this because I like this code, the source code, that is neat. And I hoped to be able to show that it is performing well. It's fast, it's no overhead. But I must admit that I did not expect this. And I checked then with other compilers, and GCC does the same, and MSVC does the same. Compilers are pretty darned awesome. This nerd heart is beating so hard right now. So I can lift the level of abstraction to write code where I'm really just saying what my intention is in a high-level way, and the compiler just figures it out. That is so neat. But there are some things to improve. I made some sheets for, well, slideware. So const expert, we should const expert everything, right? Always. Yeah, done. Because lambdas are const expert from C++ 17 and later, if they can be. You don't have to do anything with that. They just are. Good. Perfect forwarding. Of course I want perfect forwarding for everything. Conditional no except is good to have because it doesn't, rarely I would say, it helps the compiler itself to do a better job, but sometimes library writers make use of is no throw whatever. They can make more optimal implementations if they know that no exception can possibly be thrown. So the canonical example is when a stud vector must grow, if it knows that the t is no through move constructible, it can just allocate a new block of memory, move everything in, and release the old block, and everything is fine. Whereas if it may throw, this is absolutely horrible. Then what it will have to do is create a new block, copy everything in, because just in case anything throws, it must then destroy the elements that have been copied so far and deallocate and then rethrow and leave the vector where it was. So conditional no except can be a performance enhancer. And we want an explicit return type that is deduced in the type system, not in the implementation. And this goes back to the question earlier about the error messages. So we'll get to that very soon. So perfect forwarding, that is not a big deal. We have our Lambda here, which takes a number of things. We can take the function as a forwarding reference and capture it as a forwarding reference. We capture it by value, but forward it in properly. And this works fine. Perfectly, I'm not very happy about having decal type cluttering my code. C++ will give us the possibility to be explicit about the template types, which is good. It also makes the syntax for templates yet a little bit weirder. But that's the way it is. I personally prefer this. I think it's more explicit what I'm doing. But it's a matter of taste. It's functionally completely equivalent in this case. The tuple is interesting because there is absolutely no way in C++ 14 or 17 to do forwarding of a parameter pack. We could construct a stud tuple by forwarding in, but come on, we are implementing a tuple. We shouldn't implement a tuple in terms of tuple. That is daft. So this is just a sad state of affairs. C++ gives us this probably is the ugliest syntax yet in the language, but it's a way to do perfect forwarding of the capture of a parameter pack. So .t's is stood forward of the t's. So now we do perfect forwarding of each and every one of the elements that are still captured by value. And yeah, I can use explicit template parameters if I want to, matter of taste. And then we add a bunch of more stood forward and stood move and what have you. And the code is not very clean anymore, is it? I'm not happy about this. And I don't know of a way to fix it, sorry. But that was that, okay, conditional no except. So what we do is we say that this lambda is no except if the expression is no except. So we do like that. No except of func of t's. The outer no except takes a boolean and say this function is no except true or false. The inner no except is a predicate, which then checks is the call of func of t's no except true or false. And the same with the func of elements. And yes, you do really need double parentheses because no except needs its expression in parentheses and a fold expression must be parenthesized. So it's kind of ugly, but it works. And this is not good. This just isn't good. It isn't. And then we add some more of the same. Ugly repetition. And then we get to the explicit return type. like I said, this can be important to short-circuit the horrible template compilation error messages. So what we do is we say that the return type of this is the decal type of calling func of t's. And this now checks the return type when doing the type check instead of when actually doing the call, which means that, to come back to this question about compilation errors, without this, if you make the call with something where the expression isn't compilable, you get a huge spew of error saying that there is no operator equal between a string and int, for example. And you wonder why? What? Where did that come from? Whereas here it will say, sorry, there is no operator equal between any of int and string, because I could not find an operator equal between string and int. So that gives you a lot better things. But I'm sorry, I'm lost for words. This is just so bad. This is just so bad. The only thing I can say is watch this lightning talk by Vittorio Romeo from 2.5 years ago. It's titled, "You must type it 3 times." And the obvious question is, why can't the compiler do this for us? Because it can. It has all the information. Actually, there is a way around it, and that is to write the ugliest macro known to man ever. Actually, it isn't the ugliest, but it's ugly. It's a macro. And I don't want to do that in a presentation that is broadcast on YouTube and everything. So, sorry, I don't have any solutions to those. Fortunately, the last two are really for the overachievers. It's not really necessary. It does make your code better for the user. It makes life more miserable for you as an implementer. So that was Modern Techniques for Keeping Your Code Dry. I'm Björn Fahller. Remember, fold expressions are awesome. They really are. We've seen a lot of fold expressions. Std-tuple and std-apply are awesome. They help so much when you're dealing with calling functions from tuples. It's really a friend when dealing with the generic code with a lot of parameter packs. Higher order functions are awesome. They compose. You saw how extremely well they composed. These or elements greater than 0, and it's superb. You want those. Lambdas are awesome, and in C++, 20 lambdas are awesome. And compilers are awesome, as you saw. This white space position thing that blew my mind. Match Godbolts is awesome because you would not have believed me if I said that this is as efficient as it is, if I hadn't been able to show it to you. And no acceptance VNI return is full. Actually, the functionality is awesome, but the way you write the code is just misery. And sweating the small stuff makes you really, really, really annoyed, but it can lead to pretty neat code. So keep your code dry. Thank you.
We still have a chance to ask Björn.
Björn, thank you for a great talk, and I share your opinion about how awesome is the final code that the user has to write. But when you, if I was some developer in your company who first sees these abstractions, and he sees this like, if any of ABC equals 0, it's great, but can I use it? It's my question as a developer. Can I use it in this algorithm like you shown it to find white space? Will it be optimal or not? Will it, or maybe it will have a lot of overhead? So I try to look into the code of the any-of, and I see this horrible mess of no except and everything. So it looks like a problem that you still have to look into the code, and moreover, you don't understand it, because it's hard to understand it after you have written all the things.
I agree with most of what you said, except the last bit, because you can use functions without understanding their implementations. You use a lot of them, like in the standard library. I'm willing to bet, although I don't know you personally, but I'm willing to bet that you don't know how most of them are implemented, but you use them. You just trust that they work the way they should. The question about performance, in my experience, yes, they do perform exactly as well as I showed you in these examples, with one caveat, and it's an important one. It works that well when the values, in this example with the any of or whatever, when the values are already computed and known. If there is a value that must be computed, then the short-circuiting of the logical expression comes too late, because the value must already be computed to construct the any of object, and then maybe the value is not used because the expression was falsified earlier and short-circuited. So there you have a potential loss. And also there was earlier a question about more complicated, less trivial types than integers, and you need to make a little bit of a change to the code to accommodate for those. Happy with that answer?
Yeah, thank you very much.
Hi, Björn. Thanks for your talk. That was great. But I hate to be the bad guy here. Can you guess what I'm going to ask about? Compile times.
Compile times, yeah. Why do people care about that? The program
Do you want me to tell you? Oh,
no, I know. I happen to be a software developer, you know. So
me too. Yeah.
I know about compile times. That can be an issue. Yeah, it's true. I don't really have anything to say. It's sometimes the compile time loss is so minor that it's worth it. Sometimes it's prohibitive. I cannot really say more. There was a question further back.
Thank you for your talk. I have two questions. First one is, could you use concepts with the Lambda you return from functions?
Wow, I have not thought about that at all. Sorry.
Yeah, because
I haven't played anywhere near enough with the concepts to be able to have an opinion.
Yeah, because that's a way to reduce the compilation error messages in a much better way than the trailing return types. In this situation, I think it will play just great if it's possible. In the C++20, I'm not sure about that.
Yeah, true. In that situation, the concepts can play the role that the SFINAE return type logic does. So it short circuits the errors and it may make them clearer, probably, I think. But that was the first I heard about it. So tread carefully with what I say.
Yeah, the second is like kind of a joke. You cannot use your solution when your comma operator is overloaded.
Yeah, the first thing to do is to just fire all developers who overload the comma operators, and then you'll be fine. You're right, but just don't. You're right, but don't.